Hey everyone, Professor Dustin here. This video is going to be a very short introduction to a specific topic in the field of magnetism, which is forces and torques on a loop of current. So we've already studied how we can find the force on a current loop. Sorry, not on the loop, but on any length of wire if we have a current through I, by taking the length of the wire and then the cross product of the current with the magnetic field. That tells you the force, the magnitude, and the direction of the force on that wire. Well, the trick here is that if you make a loop, actually you get some sort of interesting behavior as far as the forces on the entire loop and the torque. So first, let's just define what I mean by loop. By loop, I mean an entire circuit. So a circuit that starts at one point, the current goes around and goes back to the exact other point. Now, of course, we might have a battery in there, we might have a resistor in there or something. So we're going to simplify and just talk about a loop that like enters some area and leaves some area. And actually, to start with, let's just say a loop with no battery or anything. So there's no reason this loop is like actually, being powered or actually running or a current going through it. But just to sort of start with this topic, let's just make the simplest thing possible, which is a loop with no battery or anything. There's just a loop going around. Okay, so let's put a magnetic field. Let's do a magnetic field like into the page. So there's our magnetic field into the page. And now let's look at the forces on this loop of current. So because this is a whiteboard video and I don't have like a hand, it's going to be a little tricky to do the right hand rule. So let's talk about a way of doing the right hand rule in these circumstances when you can't actually use your right hand. And that is to think about a little XYZ coordinate system. XYZ. And if you set up your right-handed coordinate system correctly, it turns out that crossing the X direction with the Y direction will give you the Z direction. That's the same pattern as we have with the magnetic field equation up there, the force equation, which is I cross B equals F. So that means that all we have to do is put a little XYZ coordinate system everywhere that there is an I, B, and an F, and with the X and the Y in the direction of the current in the magnetic field, the force will be in the direction of the Z direction. So that's sort of a trick to getting. It's another way of doing the cross product, but it's really a trick of getting it to do it in these circumstances where you can't see my right hand. So we're first going to do the force on this lower length of wire, and I'm going to do that by drawing a little XYZ coordinate system that corresponds to where I and B are is going to be the X and Y direction. So I is this way, so that's going to be the X direction. B is going to be into the page, and so then what you do in the Y, and that's the Y direction. So then what you do is you take this little XYZ coordinate system, you flip it around until you get it oriented the correct way in your brain, and you can see X that way, I in means that Z is up. And you can kind of imagine that I'm like moving the X there, which means the Y goes into the page, which means the Z is upwards, cool, and that gives me my force being upwards like that. So I want to do that in every part of the current loop, here, there, and there. Just notice that, like, okay, the I is staying the same. Let's say the length is staying the same. Let's say it's a square. But the direction of the current is changing. It's now going up instead of going to the right, so the direction of the force will be different. I won't do all four, but I'll do, like, this side real quick. If I'm going to do this, I'm going to have the I direction that way, and B is still into the page. And actually, you can see that if I just start here and then turn it to get to there, I have that the Z direction is that way and FB is going in that direction. So if I keep doing that, do the same thing up here. That means FB is inwards. And then lastly, got a little arrow there, arrow there, arrow there, and FB is that way. So cool, so that's the force on an entire loop of current, and you can see what's happening is the net force is actually 0 on this guy. So the force here is going to be opposed by the force there is going to be opposed by the force there, and if we added up all the forces, we would get that the net force is going to be equal to 0, and this loop doesn't go anywhere. It doesn't move at all because the net force is 0. Okay, but that was one particular orientation of the loop where we had the magnetic field at a right angle to all the wire lengths like this. There's another way of orienting the loop, which is having it sort of sitting in the plane of the magnetic field. So there's the same loop, but let's make the magnetic field be in the same plane, kind of like this. So now let's play the same game with the cross product. It's it's going to be pretty easy to extend from one leg to the other leg. So let's just do one leg. And again, I'm going to try to get I is going to be my x direction, B is going to be my y direction, whatever the result is going to be z. And so I'm trying to keep this like little picture of the pattern of the arrows in my head. So first, I is going to be x, so we have x this way. B is going to be y, so definitely y that way. And then if you think, how do I take this little set of arrows to get down here? You can see that z is going to be out of the page. So it's going to be pointed like that. Z. Let's just check. I'm sort of rotating x into that x and then y upwards, and then z comes out. Yeah. So the force on this part of the wire is out of the page. Okay, well, let's move our wire, let's move our calculation out to figure out what the force is on this part of the wire. But actually you can see the force on this part of the wire, the current is in the same direction as the magnetic field. So in that case, the force is actually 0 on the wire. So there is no magnetic force on the wire on that leg. Same thing over here. The current is anti-parallel to the magnetic field, so there's no current, there's no force over here either. So let's check on this side of the wire, and clearly, like, the pattern is not quite as simple as it is over here. So I'm going to be a little bit more careful. I'm actually going to redraw my little coordinate system. So x is going to be that way. Y is going to be in the direction of the B field like that. And you can see in order to do that, we have to actually flip this little picture around, and the z direction is going to be into the page. Whoops, wrong color. Into the page FB. So sorry, that's the z direction, but that means that the magnetic force is into the page. So actually the net force is still 0 here, right? The total force on this leg is 0, this leg is 0, this leg is up, this leg is down. If they're the same length, then the force on each leg is the same. So the total net force here is still 0. So we still have a net force of 0 on this loop. But now look what happens. It's actually not in equilibrium anymore, right? Over here, these up and down forces, they're on opposite parts of the loop. So here, the loop is being pushed upwards. It's being pushed downwards. Here, the loop is being pushed upwards. That's unlike the situation over here where the forces were directly opposite from each other. And so there's really no motion here. But here, this loop is gonna spin, right? Because there's an opposite force on two opposite sides of the loop. If I redraw that with those these two forces sort of highlighted at an angle so we can see these forces, you're going to see what's going to happen. So now the current loop is sort of in the plane, sort of going into the page, right? The I is here, and the magnetic field is going to the left. But now it's easier to see that the force on that side is upwards, and the force on this side is downwards, and this thing is going to move in some kind of rotating pattern. So normally what we do is we like fix a rotational axis here. So you fix some kind of axle through the motor that way, and so the thing actually spins in this fashion. It spins that way. This is how you actually get electric motors, is you actually have little current loops which are, fixed to spin on axes, and the opposing forces are on two opposite sides of the axis. Now, you can see what's going to happen that's kind of tricky is when this thing spins halfway, meaning the loop is now oriented like that in the magnetic field, it's actually going to be in this situation. So we actually have to be a little tricky if we want our motors to continue to move, because they'll just flip into this position and be in static equilibrium, right? So we have to talk a little bit about how we actually get motors to move. We have to switch the current direction to get them to move past the equilibrium point, which we'll talk about that. But this is how you get, this is the basics behind generators and motors, is getting forces on opposite sides of loops to spin in the magnetic field. Of course, there's also a torque on this loop, because in this position, those forces are acting a distance away from the axis, so we're going to have to actually use the torque equation. So remember the torque equation, which is that the torque is R cross F, where R is the distance from the point of rotation, and F is the force being applied. So now that we have these forces that act different directions on different parts of the loop, we're actually going to have to worry about the torque equation, because the torque equation is how things rotate. It describes how things rotate, and that's what we have rotating in these magnetic fields. Okay, cool. So that's a quick introduction to forces and torques on the current loop. The key thing that's happening is as the current direction changes, the direction of the force changes, and in certain positions, you can get loops that want to move in the magnetic field just by themselves. That creates forces, and it can create things like motors to allow you to drive other things. So you just have a magnetic field and some currents, and you can get like an electric motor, like in a car or something. A generator is the opposite. We actually won't really go into generators carefully, but in a generator, you have a loop, and then you drive it. You crank the loop through the magnetic field, and that actually generates a current. We won't do that until we get to Faraday's law, but it's the opposite of a motor. In a motor, the motor spins to create the thing you want to do to drive your car. Whereas for the generator, you do the spinning, that moves the wire through the magnetic field, that creates the current, and so you generate electricity that way by creating the current out of the motion of the wire through the field. Okay, that's it. We'll talk more about this in class. Thanks very much. Take it easy. Bye.